We are currently chasing a computational milestone. Quantum computers promise to unlock processing power so massive it could solve problems our current supercomputers would need millennia to crack. But there is a significant physical roadblock. To get these quantum processors to function at all, their internal environments have to be cooled down to near absolute zero, a temperature colder than the vacuum of deep space. Maintaining that level of extreme cold requires energy-intensive infrastructure. For decades, physicists generally accepted this thermal barrier as a strict limit of nature, a constant constraint in the development of quantum technology. Achieving these same results at standard room temperature is the definitive objective. Removing the need for extreme cooling would remove the largest bottleneck in the development of practical quantum systems. The breakthrough that addresses this freezing problem didn't come from a computer lab. It started with researchers looking at the everyday physical properties of a common metal, silver. A team of scientists at Brown University and the University of Michigan were investigating a century-old mystery in material science, specifically how the internal structure of metals shifts and transitions under heat. During their experiments, they managed to physically assemble and stabilize a transitional state of matter. It is a structural arrangement so unstable that theoretical models previously suggested it could only exist for fleeting fractions of a second. By capturing this specific structural phase, they engineered a material that exhibits the exact quantum behaviors needed for computing at room temperature. When heated, metal atoms undergo a structural transition. They shift from a tightly packed heavy cube into a looser grid. If we could freeze time the exact millisecond those atoms are shifting, what would that intermediate geometry look like? The leading explanation is the Nishiyama-Wassermann pathway. This theoretical model mathematically predicts the specific shape of this intermediate ghost phase. In nature, this phase is practically impossible to study. It's highly unstable, lasting only a moment before the atoms settle into their final permanent positions. Because the researchers could not observe this phase in nature, they decided to build it manually, forcing the atoms into that exact intermediate arrangement from the bottom up. They synthesized customized silver nanoparticles, called mecons. By controlling heating conditions, they shaped these particles into 14-sided objects, sitting geometrically between a sphere and a cube. Next, they coated the mecons with flexible molecular chains, allowing the particles to bond. Those flexible chains gave the silver particles freedom to shift. The 14-sided geometry allowed the mecons to slide and lock into a single ordered superstructure. Analysis of this superstructure revealed that the internal arrangement matched the unstable transitional phase predicted by the Nishiyama-Wassermann model. By stacking these nanoparticles like nanoscale bricks, the team took an inherently fleeting phase of matter and stabilized it as a permanent material. Stabilizing that geometry was a significant structural achievement. But when the team exposed the silver superlattice to light, they observed a reaction that had never been seen in a metal at these temperatures. The material displayed deep, strong light-matter coupling. This is a phenomenon where the electrons inside the silver nanoparticles oscillate in perfect synchronization with the external light waves. This synchronization indicates the light and electrons operate as a single unit. They've become quantum mechanically entangled. This sensitive quantum effect typically disappears unless the material is kept at absolute zero. Yet, this engineered silver held the entanglement at standard room temperature. The discovery demonstrates that stable, observable quantum phenomena are not physically restricted to absolute zero environments. Removing the requirement for extreme cooling changes the feasibility of quantum engineering in real-world environments. This provides a path toward quantum processors that bypass expensive cryogenic infrastructure, as well as new categories of high-precision sensing technologies. The discovery has an ironic origin. A study on the structural geometry of shifting metal accidentally provided the physical architecture for a room-temperature quantum material. It shows that the next advancements in material science will come from identifying and stabilizing these transitional states that were once considered too unstable to exist.